We've looked at how we can take the equation of a line, that is a linear equation in two variables, and graph the set of solutions to that equation, which forms a line in the coordinate plane. What we want to do now is go sort of the other direction. What if we know about a line, know some things about some line in the plane, and we want to find an equation whose solution set is that line? So that's going to be our goal for today, is figuring out how to come up with an equation given a line and see how we can use that to more efficiently graph lines when you have their equations in a particular form. So let's look at the following example. Let's find the equation of the line with slope 3 and y-intercept 0, -2. Let's sketch out what our situation is. Oh, sorry about that. Let's sketch out what we've got here. Well, we've got our line, and we know one point on the line right away. We're told that the y-intercept of this line is 0, -2. And that means that we know that this line that we're looking at passes through that point 0, -2. Means that the point 0, -2 is where the line that we're looking at passes the y-axis. Then we're told that the line has slope 3. Now we know from what we looked at last time that that means that the line is going to be sloping upwards as we move from left to right, because this slope is positive. And so now we want to say, all right, well, what more can we figure out about this? We want to come up with some sort of equation that has a solution set of precisely these points on the line. We want to find an equation to go along with this line, inverting the process that we were using before. So the way that we're going to do that is we're going to take a point on the line here, and we'll go ahead and just call it x and y. We want this point to be able to stand for any of the points on the line that we like, so we don't want to give it any particular values, just leave it as x and y. But the things that we know about our line are going to be able to tell us a relationship between the x value and the y value of all the points on this line, which will turn into precisely the equation of the line. So we know that the slope of this line is 3. So we know that m is equal to y2 minus y1 over x2 minus x1 is the slope equation, where m is the slope, x1, y1 is any point on the graph, and x2, y2 is any point on the graph. Now, for our specific example, I want to let x comma y be the x2 and y2. And I want 0, -2 to be the x1 and the y1. And we know that the slope is 3 because that was given to us in the problem. So if we plug all of these values in, we get that 3 is equal to, now y2 is just the y, where this y corresponds to the y-coordinate of the general point we're looking at, minus y1. Now y1 was -2. That's the y-coordinate of the y-intercept that we've got here, over x minus Now x1 was 0. So we've got an equation now that relates x and y together. And it turns out that this is an equation of the line. Now, of course, this is not super useful right here. Let's go ahead and simplify this down a little bit. If we simplify this, we get that 3 is equal to y plus 2 over x. We can multiply x on both sides. Get 3x equals y plus 2. And now, in order to see how the graph relates to the equation, I want to subtract 2 from both sides. And I'm also going to switch the order of the equation. So I'll have y equals, and then the other side of the equation becomes 3x minus 2. Now, what's useful about this process is that there's nothing really special about the number 3 that we used for the slope. This same computation would work kind of no matter what m was. So this 3 that shows up as we go through this process, well, this is exactly just m, the slope. Furthermore, because we were looking at the y-intercept here, this -2 made its way through the problem and got here to give us the y value of the y-intercept. And it turns out that this is no accident. In fact, if you take a line with any slope with a given y-intercept, you can always write down the equation, or an equation, with that line as its solution set using those two numbers. So this is what we're going to call slope-intercept form. And let me define that precisely. The slope-intercept form of a line, or I should say of the equation of a line with slope m and y-intercept of 0, b is y equals mx plus b. So this is what we call the slope-intercept form. And it's called that because the slope and the y-coordinate of the y-intercept can be read off directly from the equation. So we have y equals mx plus b. So for example, if I look at the equation y equals -2x plus 7, I can read off what the slope and the y-intercept of the line that is the solution to this equation immediately just from the equation itself. So this -2 here is the coefficient of x, and that's also going to be the slope of the line. The constant term is the y value of the y-intercept. And so we can say that this equation that we've got has a solution set, which is a line, and that we can sketch out approximately. We can say that it's going to have a y-intercept of 0, 7. 7 because that's the constant term in the expression on the right. And then it's going to have a slope of -2, which for the moment we'll just sketch out this way as a downward sloping line. So this is what we can get from the equation of a line that's written in slope-intercept form. A warning. You must solve for y completely, meaning it has to just be y on the left-hand side of your equation before you can read the slope and y-intercept. From the equation. So this is one of the forms of the equation of a line that we work with most often. We already saw the standard form of the equation of a line a few sections ago, and that form, you can't immediately read any of the graphical properties of the line off of it. You can't tell the slope immediately or the y-intercept the way that you can do here. The slope-intercept form of the line really is the most efficient way of recording the graphical information about the line. So let's look at another example. Let's find the slope-intercept form of the equation of the line passing through 0, 3 and 1, 7. Now this problem is a little bit different because we haven't been told the slope precisely. In order to write down the slope-intercept form, y equals mx plus b, we need two pieces of information. We need to know the slope of the line, and we need to know the y-coordinate of the y-intercept. And usually, when you're working problems, you will not know both of these. Sometimes you won't immediately know either one. Now in this problem, we do have one of these immediately. We have the y-intercept of this line. We know that the y-intercept of this line is 0, 3. And we know this because the y-intercept is always a point of the form 0, something. So if that point happens to be given to you or you know it somehow, you can always just use it as the y-intercept. So in our problem, b is going to be equal to 3. But that only gets us halfway. We also need to know the slope of the line. In this problem, we haven't been told the slope of the line, but we have been given enough information to figure it out. To figure out the slope of a line, we just need 2 points on the line, and that is what has been given to us. So, to find the slope m, we're going to use the slope formula. And write m is equal to, and now we have to take the difference of the y values on top divided by the difference in the x values. So the y values are as follows. We get 7 minus 3, and then the corresponding x values are 1 minus 0. So we get m is equal to 7 minus 3 over 1 minus 0, which is 4 over 1, which is 4. So this tells us that the slope of this line is 4. So that means that our answer can be written as follows. Y equals, now m is 4x plus the y-coordinate of the y-intercept is 3. So that's the slope-intercept form of the equation of the line passing through the points 0, 3 and 1, 7. So now let's look at what happens when you don't have the y-intercept immediately given to you. Let's find the equation of the line passing through -2, 3 and -4, 10. So in this problem, I should specify we want the point slope form. Slope-intercept. I'm getting ahead of myself. We want the slope-intercept form of the equation of the line passing through through 2, 3 and -4, 10. So again, we want y equals mx plus b, but we don't know what b is. We're not told the y-intercept of this line. We're told 2 points on the line. We could graph out the line, but neither one of those points are the y-intercept. So in this case, we need to use the slope. We need to find the slope first. Now, sometimes in a problem like this, the slope will be given to you. Sometimes you'll be given the slope and a point, but that point won't be the y-intercept, and you'll have to use this process, but you'll start one step later because you won't have to go through the first step we're about to go through, which is finding the slope. If you do not know the slope of the line that you're working with, that is almost always the first thing that you want to try to figure out. So let's figure out the slope. M will be, now we want the difference in the y values, 10 minus 3, and then the difference in the x values, making sure to keep the same order. So 10 and -4 go together as a y and an x, and then 3 and 2 go together as a y and an x, and so this is the correct way of calculating the slope. So 10 minus 3 is 7, -4 minus 2 is -6, so we get -7/6 as the slope of our line. So that means that we're halfway there. Now let's go ahead and write down what we have so far. We know that y is going to be equal to -7/6 x plus b. And we know that this equation is going to be true for all points on the line, for all x and y points on the line. And we're going to use that to figure out what b is going to be. So at this point, what we want to do is to use a point that we already know is on the line. We want to plug it into the equation, the partially formed equation that we have right now, and then solve for b. The idea here is that, again, this equation, the equation that we find at the end of the day, will have to be a true equation, will have to be a true statement, no matter what point on the line we plug into it. So in particular, we can pick one of the points that were originally given to us, either the 2, 3 or the -4, 10, and plug them into this equation, and we know it has to be true. So I'm going to choose to plug in 2, 3. You could plug in either one of these and they would both work and give you the same answer, in fact. So if we plug in 2, 3, we'll get 3 is equal to -7/6 times 2 plus b. And now we're going to solve for b. Now simplifying this down a bit, the 2 and the 6 can cancel, leaving just 7/3 behind. So we get 3 equals negative 7/3 plus b. I'll add 7/3 to both sides. Now 3 is 9/3, and 9/3 plus 7/3 will be 16/3, and that'll be equal to b. So that tells us what our b is. That tells us, in fact, the y-coordinate of the y-intercept. So this tells us that the y-intercept is 0, 16/3. So for our final answer, we have that y is equal to m. M is the slope, we figured that out. Negative 7/6 times x plus b, the y-coordinate of the y-intercept, which is 16/3. So this is the equation of the line that passes through the points 2, -3 and -4, 10. So let's see how we can use our newfound knowledge to more efficiently graph equations when we can put them into the slope-intercept form, y equals mx plus b form. All right, so let's look at graphing lines of the form y equals mx plus b. The idea behind this strategy is the following. When we have a line of the form y equals mx plus b, we can immediately see one of the points on the line. So immediately we're going to plot the point 0, b, the y-intercept, because we know that's there. And then we'll use the fact that the slope is equal to rise over run, or the change in y over the change in x. And starting from the point 0b, we'll move to the right by delta x, and then up or down by delta y. That's going to depend on whether the slope is positive or negative, to find another point. So let's see an example of how this goes. Let's graph y equals 2/3 x minus 1. I'll do that here. And actually, let me go ahead and make my plot nice and big. All right, so first step, we want to plot the y-intercept. The y-intercept for this function can be read from the constant term over here on the right. So the y-intercept is going to be our point 0, -1. And that's going to be sort of our starting point, our anchor. Everything that we do next is going to be based off of this. And now we're going to look at our slope 2/3. So we have that our slope is 2/3, which is the rise over the run. And so what that's going to mean for us is that to move from one point on the graph to another, we want to move 3 units to the right, then 2 units So the denominator of your slope tells you how much your x coordinates should change, how far you should move horizontally. And then your numerator tells you how far you should move vertically. So starting from the point that we have, 0, -1, we're going to move to the right by 3 and then up by 2. So we start at 0, -1. We move to the right by 3. That gets us to 3, -1. And then we move up by 2 in order to give ourselves the point 3, 1. And that's another point on the graph. Now, technically 2 points is enough to graph a line, but often we want more, just especially if we're doing this by hand, just to avoid any errors. So we can do the same thing again. We can continue this process by moving another 3 units over to the right to 4, 1, 5, 1, 6, 1, and then up another 2 units to get to the point 6, -3. I'm sorry, I don't know why I said negative. It's definitely not negative, it's definitely positive. And so these three points here all lie on our line. And so we're able to graph that out. Let me move that into position. And that's what the graph of our solution looks like. So as you can see, the strategy for graphing a line that's written in y = mx plus b form is basically the same as what we had before. We're still plotting points and connecting them up. The point is, when the problem is written in y = mx plus b form, it's a lot easier to actually write down the points. You can find one point immediately, and then you just have to move over and up or over and down a couple of times to find a few more points to use to graph it. So let's do another example with this. So let's graph 2 times y plus, 2 times y plus x equals x minus 3. So the thing to remember about graphing lines using the slope-intercept form, which is the most efficient way of graphing it, is that the first step is to actually put it into slope-intercept form. So step 1 is we want to put into y = mx plus b form, i.e. we want to solve for y. So we start 2 times y plus x equals x minus 3. Distributing the 2 on the left gives us 2y plus 2x equals x minus 3. We'll want to get y by itself, so we'll subtract 2x from both sides. Get 2y is equal to -x minus 3. And then we'll divide everything by 2. You'll notice that when I've done this, I've divided each term on the right by 2. And that's because I want to keep them separate, because I want to be able to determine my y-intercept, and I want to be able to determine my, my slope easily. So we get y equals -1/2 x minus 3/2. So notice what I've done here. -x over 2, that's the same as -1 over 2 times x over 1. And then we can write x over 1 as simply an x. So I'm writing it this way in order to make it really clear what's what. So we see that our slope is now negative 1/2, and our y-intercept is 0, comma, negative 3/2. So let's use this to graph our line. All right, so first thing to do is we want to graph our y-intercept, which in this case is at 0, comma, negative 3/2. Now 3/2 is the same as 1/2, so there we go. There's our y-intercept. So next we want to deal with our slope. Now, when dealing with negatives, what you want to do is you want to attach this negative to either the numerator or denominator. It doesn't get attached to both of them. And so we could write this either as negative 1/2, or we could write it as 2 over negative 1. And sometimes we'll want to use either one. So we'll see that in a second. At first here, let me go ahead and write it this way, as negative 1/2 for the rise over the run. So what this means is that to get from one point on my graph, like the y-intercept we have plotted, to another, I need to move to the right by 2 units and down by 1 unit. Down because that negative 1 is negative. So I'm going to go to the right by 2 units, and then I'm going to go down 1 full unit. Now, because my point was halfway in between a couple of integer marks on the vertical axis, when I shift exactly 1 down, I'll still be halfway. And so moving over by 2 and down by 1 gets me to the point 2, comma, negative 5/2. And I could do the same thing again. I could move over by another 2 and down by another 1 and get to this point here, which would be 4, comma, negative 7/2, and continue on, get as many points as I like. And get points there. Now, you'll notice that I'm starting to approach the edge of the graph. This sometimes happens. Sometimes you'll have a line with a negative y-intercept and a negative slope that goes down this way. So in that case, what you can do is try moving this negative to the other position. And so we can also write that the rise over run is equal to 1 over negative 2, because that's another way of writing the slope. Now in this case, working on the right-hand side here, where the rise over run equals 1 over negative 2, in this case, the run is negative 2, so we'll be moving to the left by 2. A negative value here indicates that you want to move to the left rather than the right. And then a rise of 1 means we want to move up by 1. Positive values of the numerator in your slope always mean move up. Negative values in the numerator mean move down. Positive values in the denominator mean move to the right. Negative values in the numerator mean move to the left. And so that gets another point over here, working backwards, of negative 2, comma, negative 1/2. And we could even go further and get up here to negative 4, comma, 1/2. So we can use this process to find a bunch of points very efficiently, much more efficiently than the methods that we had before, and graph out our line that way. So that's how we can use the slope-intercept form of an equation of a line to graph it efficiently. The fact that we can determine the slope of two lines easily using the slope-intercept form also helps us to determine whether lines are parallel or perpendicular or neither. So recall two lines are perpendicular. Let me start with parallel. If their slopes are equal. Two lines are perpendicular if their slopes are negative reciprocals. So, we already knew how to take two lines and determine whether they were parallel or perpendicular, but now we have a much faster way. So, let's take the example. Are the lines determined by y equals 1/3 x plus 6 and 3y minus x equals 4, parallel, perpendicular, or neither? Well, the answer to this is going to come from the slopes, and so we want to put both of these equations into slope-intercept form. Now, our first equation here is already in slope-intercept form, and in fact, we can tell that this line's slope is 1/3. So let's work on the other one. We've got 3y minus x equals 4. Let's add x to both sides. Get 3y equals x plus 4. To get it into y equals mx plus b form, we're going to divide everything by 3 and get y equals, now x over 3, I'm going to use the same notation again to write x over 3 as 1/3 times x. So here is the y equals mx plus b form, the slope-intercept form of the second line. And we can see that this line also has a slope of 1/3. Now, we do need to check one thing here, and that's to make sure that we actually have two different lines. And the easiest way to check that, if they have the same slope, is to look at their y-intercepts. A line that's not vertical can only have one y-intercept, which means that if you've got two lines with different y-intercepts, they have to be different lines. So our first equation up here defines a line with a y-intercept of 6, and our second line has a y-intercept of 4/3, therefore they are different lines, but they have the same slope. They both have a slope of 1/3, and so our answer is that they are parallel lines. To come back to what I was saying about checking to make sure that they are actually different lines, let's imagine that the second equation was of this form, 3y minus x equals 18. Let's say we put this into slope-intercept form. We get 3x is equal to x plus 18. Divide everything by 3, and we get y is equal to 1/3 x plus 6. So what that means is that the equation y equals 1/3 x plus 6 and the equation 3y minus x equals 18, these both define the same line. So in particular, they are not parallel. Parallel lines have to be different lines. A line is not parallel to itself. So that's not something that comes up a whole lot, but keep an eye out for it. In order to say that two lines are parallel, they need to actually be different lines. And if they have the same slopes, you can determine that they're different just by comparing their y-intercepts. So now we want to talk about the third form of the equation of a line that we will work with. We've worked with the slope-intercept form. We've introduced that this time. We've also seen the standard form of the equation of a line reasonably often. And so now I want to look at another one which works really well when you're given a point and a slope, or just 2 points, and especially when neither one of those points are the y-intercept. So let's look at the following example. Let's find the equation of the line, or I should say, find an equation of the line with slope negative 1/4 passing through the point 5, 9. Let's sketch out what's going on again. Now, we already saw earlier in this talk how we can find the slope-intercept form of this line by using y equals mx plus b. We know what the slope is. It's negative 1/4, so we could just plug that in and then plug the 0.59 in and solve for b. However, I want to look at another way that we could do it, which is often a simpler one. So let's sketch out what's going on here. We've got the point, and I'm going to be a little loose with my points here. Just want to get them in approximately the right position. We've got the 0.59, and we know that our line is passing through that point. We also know that the line has slope 1/4, which means that it's going to be sloping downwards, but sort of shallowly, because negative 1/4 is still close to 0. So this is what our line is. And I want to do the same sort of thing that we did back at the beginning of the talk with using the slope formula, comparing the 0.59 to an arbitrary other point on the curve, on the line. So, again, we have that the slope formula says that m is equal to y2 minus y1 over x2 minus x1. And again, I'm going to use the xy point as my x2, y2, the 5, 9 point as my x1, y1. So, and we also know that the slope is negative 1/4. So that means that we get negative 1/4 is equal to, now y2 was just what we called y, y1 was 9, x2 was x, and x1 was 5. Now what I want to do here is I want to multiply both sides of this equation by x minus 5. That's going to give us, I'm also going to switch it around so that I've got the y expression over here on the left. Y minus 9 is equal to negative 1/4 times x minus 5. And this is another form of the equation of the line. This is what we're going to call point-slope form. And it's called that because it gets built out of two things. The slope-intercept form of the line, y equals mx plus b, was built out of the slope and the y-intercept. The point-slope form is built out of the slope and some point. So notice that in this setup, this negative 1/4 here is the slope. And again, if I replace that negative 1/4 with any other number, that number would still show up in this position. And then my 5 and 9 that went along with, that came from the point that I had up here, show up in these two positions for the equation. So usually when you are given a slope and a point for a line, and you want to find an equation of the line defined by those, usually the point-slope form of the equation of the line is the easiest way of getting to an equation. So let's define this and then do a few examples. So the point-slope form of the equation of the line passing through the point x1, y1 with slope m is the following form. Y minus y1 is equal to m times x minus x1. Now, it's really important when you go to apply this to remember that when you're building the equation, the x and the y, they are going to stay as variables. The y1, m, and x1, these all get replaced with the appropriate numbers for your problem. So let's take an example. Let's find an equation of the line passing through the point 1, 2 with slope negative 5. With the point-slope form, this question is really easy to answer. We're going to use the form y minus y1 equals m times x minus x1. Now, in this problem, the slope has been given to us. The slope is negative 5. So there we go. Now, the y minus and x minus, they stay as just y minus and x minus. They don't get replaced with anything. The x1 and the y1 are the coordinates of some point that the line passes through. So we know that our line passes through the point 1, 2. So that means that x1 is 1 and y1 is 2. So this gives us a form, the point-slope form of this line. Now, I should point out that every line has infinitely many points that it contains. And this means that every line has infinitely many different equations corresponding to those various points on the line. So I used the point 1, 2 because it's the only point that I know on this line. But if I happen to know some other point that was also on this line, I could have used that to develop the point-slope form of the equation of this line. Let's see how that goes in another example. Let's find an equation of the line passing through negative 3 comma 1 and 7 comma negative 5 in point slope and slope intercept forms. So when you are given points, if none of the points that you're actually given are the y-intercept, you should usually start with the point slope form. It's a much easier equation to write down than any of the other ones that we work on. So let's focus on the point slope form first. Now again, as the name suggests, to get an equation in point slope form, I need a point on the line and I need the slope of the line. Well, I don't have the slope of the line, but I do have 2 points, and that's enough to figure it out. So step 1, as always, is to find the slope of the line. So I'll take the difference in the y values, so negative 5 minus 1, and then the difference in the x values, so 7 minus negative 3. That gives me negative 6 over 10, and then I'll simplify that down to be negative 3/5. So now we have the slope of this line is negative 3/5. So let's use the point slope form. We want to take y minus y1 equals m times x minus x1. We know the slope is negative 3/5, and then the x minus and y minus stay as they are. They stay as x and y. And then we need an x1 and a y1. So these correspond to some point on the line. So which point do I use? It doesn't matter. Either one can work. So let me go ahead and do it both ways, and we'll see that it doesn't actually make any difference at the end of the day. So I'll do 2 columns here, and over here on the left I'll take negative 3 comma 1 as the point that I work with, and on the right I'll take 7 comma 5 as the point I work with. Now if I take negative 3 comma 1, that means I get y minus 1. It's always y minus the y value, and then x minus the x value over here. And then for 7 and negative 5, we get y minus negative 5 equals negative 3/5 times x minus 7. So, expanding these out, or rather just simplifying the double negatives, we get y minus 1 equals negative 3/5 times x plus 3. And we get y plus 5 equals negative 3/5 times x minus 7. And either one of these 2 equations are perfectly good answers to the question, find an equation of this line in point slope form. Both of these are equations of the line in question in point slope form. Now, how do we get slope-intercept form? To get slope-intercept form, we solve for y. And that'll apply no matter which point we started with. So, let me do the left-hand one first. We'll get y minus 1 equals, distribute the negative 3/5 through. We get negative 3/5 x, and then negative 3/5 times 3 gives us negative 9/5. Now, if I add 1 to both sides, we'll get y is equal to negative 3/5 x, negative 9/5 plus 1. 1 is 5/5, so this will be negative 4/5. fifths. So we get the slope-intercept form of the line over here on the left. Now let's do it with the right-hand side. We get y plus 5 is equal to negative 3/5 x. Now negative 3/5 times negative 7 will be positive 21/5. Then we subtract 5 from both sides. We get y is equal to negative 3/5 x plus now, or rather, not that yet, negative 5 is negative 25/5. So 21/5 minus 25/5 is negative 4/5. And what you'll notice is that we got exactly the same equation on both sides. The point-slope form of the equation of a line is not unique because there are many different points on the line. The slope-intercept form of a line is unique. There's only one slope that any line has, and there's only one y-intercept it has. And so no matter which of these points that we used, or even if we used a third point on the line to find our point-slope form, we could still arrive at the same slope-intercept form. And in particular, this might now allow us to graph out the line, because we could plot out the y-intercept and we could use the rise over run of the slope in order to get more points. The point-slope form is very useful for a certain kind of question that asks you to find equations of lines that satisfy certain conditions. So let's look at the following. Find an equation of the line perpendicular to that defined by 3x plus 2y equals 1 and passing through the point 2, negative 1. So we want the equation of a line that's perpendicular to a line that we're given the equation for and that passes through a given point. Again, the things that we need to find the equation of a line are always a point and the slope of the line. We are told a point that the line we're interested in has to go through. It has to go through the point 2, negative 1. We need to figure out what the slope is. That is going to come from this part of the problem. We want the line perpendicular to the line defined by 3x plus 2y equals 1. Now we know that two lines that are perpendicular have slopes that are negative reciprocals of one another. Therefore, if we can find the slope of the line 3x plus 2y equals 1, that will tell us what the slope of the line we want is. So let's find the slope of 3x plus 2y equals 1. And again, the easiest way to do this is to find the slope-intercept form of this line to solve for y. Let's subtract 3x, get 2y is equal to 1 minus 3x, and let's divide everything by 2, and we'll get y equals 1/2 minus 3/2 x. Now, I've written it this way because we often run into equations of lines that are written this way. We still consider this to be in slope-intercept form because all that we've done is we've changed the order of the terms. We've put the x term second, and then the constant term first. The thing to remember is that the coefficient of x, which includes any negatives in front of it, is always equal to the slope. So that means that the slope of this line, 3x plus 2y equals 1, is -3/2. Now that means that the slope of our line, the line that we're trying to find, has to be the negative reciprocal of -3/2, i.e. 2/3. So we take the reciprocal of the fraction and we change its sign. So we're looking for a line with a slope of 2/3 and that passes through the point 2, -1. So we can use the point slope form with the slope being 2/3 as we just found, and then x1, y1 being 2, -1, the point that we're given at the beginning. So we get y minus -1, the y value of our point, equals 2/3, our slope, times x minus x1, the x value of our point. So we get y plus 1 equals 2/3 times x minus 2. And this is an equation of the line perpendicular to the line defined by 3x plus 2y equals 1, and that passes through the point 2, -1. Now, some problems will then go further and say, oh, give it to me in slope-intercept form or something like this. If the problem asks you for that, you would simply take this equation and solve it for y. If you solve it for y, then you have it in slope-intercept form. All right, the last topic for today is a particular kind of real-life application problem that uses linear functions and this type of process. Let's look at the following example. A car costs $30,000 new and depreciates linearly for 10 years, at which point it sells for $2,500. Find the equation relating y, the price of the car, the value of the car, I should say, to x, its age in years. So, the key word here that lets us do anything with this problem is, of course, the word linearly. Now, the notion of depreciation is that physical objects, machines, over time become less valuable. A car that was made 10 years ago is not nearly as expensive as one that was made today. And so in this problem, we're given a particular car that we're looking at, and we want to find the equation that relates the car's age to its value. Now, whenever you're working on a problem like this, remember you always need two pieces of information. To find the equation of a line, you always need a point and a slope. Now, the slope isn't always given to you, but you can find it if you have 2 points, one of which can be the point that you're using to make the line. So you always either need to be given 2 points or a point and a slope in your problem in order to be able to solve it. In this case, we are given 2 points. We're given information about the car at 2 different points in its life. We're told that it costs $30,000 when it's new, and then after 10 years, it's worth $2,500. So what we want to do is to represent those 2 points on the graph of the value of this car in points, and then find the equation of the line that contains those 2 points. So the new value of the car. When the car is new, it is 0 years old. So when the car is new, when x is 0, the y value is $30,000. And then we're given another value. I'll just call it the old value. We're told that when the age of the car is 10, when the car is 10 years old, the value of the car is $2,500. Well, now we have 2 points. And as long as we have 2 points, we are able to find the equation of the line containing those 2 points. So, of course, the first thing to do is to use the slope, or is to find the slope. So the slope will be given by the difference in the y values. So I'll go 30,000 minus 2,500 divided by the difference in the x values. Now make very sure that you're doing these things in order. It's very easy in this situation to write 10 minus 0 in the denominator, but that's not correct. I wrote 30,000 first on top, which means I need the x value corresponding to 30,000 first on the bottom. So 30,000 minus 2,500 over 0 minus 10. So this gives me 27,500, whoops, too many zeros, over negative 10, which I can simplify down to negative 2,750. So there's our slope. Now, where we go from here depends on whether or not we know the y-intercept of our line. If we do, then we can go straight to the slope-intercept form. If we don't, then we should probably use the point-slope form and then rearrange it into slope-intercept if we want to. In this problem, we do know the y-intercept because we've got this, we have the point. We have the y-intercept. So we can use the slope-intercept form to say that y is equal to m is the slope, negative 2750 x, plus b, remember, is the y-coordinate of the y-intercept, which is 30,000. So here's our answer. Y equals negative 2750x plus 30,000. Now, when we do this, the numbers that we get are usually not random. They usually have some meaning within the problem. So, for instance, we can see that the y-intercept of 30,000 here pretty clearly corresponds to the value of the car when it was new. We can see that throughout. But then we've got this other negative 2750. And to interpret this, we've got a few ways we can think about it. One of the best ways is to start thinking about the units that go with these various numbers that we're writing down. Now, often in mathematics, we're a little bit loose about our units. We probably shouldn't be. The physicists and the engineers tend to be better at it than we are. But if you do keep track of it, it's often very helpful for telling you insight as to what the numbers that you're actually finding mean. So for instance, when we calculate our slope here of negative 2750, we took the difference of 30,000 minus 2,500. But what sorts of units are they? 30,000 what? 2,500 what? Well, they're dollars. So the unit on top of this slope is dollars. And then in the denominator, we have x, and x is being measured in years. So we were taking its price at 0 years old and 10 years old. So our slope has a unit of dollars on top and years on the bottom that corresponds to a unit of dollars per year. Now, once we write that down, then interpreting this negative 2750 becomes more easy. Negative $2,750 per year tells you that this is how much value the car loses each year. So every year that goes by, the car loses $2,750 of its value. And that's a number that wasn't given to us originally, but that we found going through the process. And this is something that often happens when we work on problems like this. We'll have numbers popping up. It won't be immediately obvious what they are, but when we think about them a little bit and give them their units, put them in the proper context, they'll give us some insight into what they actually mean.